Hi and welcome to this session, which is part of our series related to Monte Carlo simulation of valuation models. In the previous sessions, we discussed how to best account for uncertainty in our estimates of the inputs, like the growth rates, cost of capital, and so on in valuation models. We discussed that perhaps the best way to deal with these uncertainties is to model them as a random variables that are drawn from a probability distribution and simulate the model for many times and see how the distribution of value per share looks like. We saw how we can easily code the simulations in Python and keep our model in Excel. In addition, we learned how to generate nice outcome plots and statistics and how to copy them in our Excel file, and finally how to put them in a nice format there. Now in this session, I would like to talk about 3 or maybe 4 most important probability distributions that, if you know, is almost sufficient when modeling your inputs in a Monte Carlo simulation of a valuation model. I will also talk about which of these distributions are most appropriate for our input variables and how to decide about choosing a distribution and the parameters for your variables. We will talk about the following distributions in this session: normal, log normal, uniform, and triangular distributions. Let's start with the one most of us are at least familiar with its name, which is normal distribution. Many variables could be modeled as being drawn from a normal distribution. Normal distribution is a symmetric distribution and it's symmetric around the mean. In a normal distribution, the mean, median, and the mode of the distribution are the same. We have another parameter in a normal distribution, which is the measure of dispersion around the mean. This is called the standard deviation. So to illustrate this better, let's generate numbers from a normal distribution and plot the histogram showing the distribution of the numbers. As you see, I am using Jupyter Notebook to help me generate the plots and illustrate the ideas I am going to discuss in this session. If you are new to Python programming in Jupyter Notebook, you can check the first video in Monte Carlo playlist here in this channel that shows how things work in the notebook. I also provide the link to the description of this video just in case. So let's generate numbers from a normal distribution. To do so, we can use NumPy, random, and normal, and then we need to pass the mean, standard deviation, and the size. Let's generate numbers from a normal distribution with a mean of 20% and a standard deviation of 5%, and let's generate 1 million numbers from such a distribution. Then we can define how many bins we would like the histogram to have, and we set the density to true, not to show us the numbers, and instead the density. Okay, let's show the histogram. As you see, the mean is 20%, which is also the number with the highest likelihood of happening, which is the mode of the distribution. It's also the median of the distribution, since half of the numbers are on the right side and half are on the left side, and therefore it's a symmetric distribution. So now, with these characteristics of the distribution, you should know what kind of variables you should model using a normal distribution. You need to be relatively confident about the mean or the most likely outcome. And the positive and negative deviation from this average value should be equally likely. For example, imagine you want to project the growth rate for a company for the next 5 years, and you have strong reasons to believe that the growth rate will be around 20% each year. So the most likely growth rate is 20%. But you are not certain about this, and you believe that the actual growth rate with a very high likelihood will be in the range of, say, 10% and 30%. And as we go further from the most likely outcome, which is 20%, the probability of realizing of those growth rates would fall sharply. In that case, you can model the growth rate as a normally distributed variable with a mean of 20% and a standard deviation of 5%, exactly like the one we have here. You may be wondering, how did I come up with 5% standard deviation that serves me well in this situation? The answer lies in the characteristics of a normal distribution, which is super important to know. In a normal distribution with probability of 95%, the numbers would be within 2 standard deviation on each side of the mean. So to apply it in this example, since the standard deviation is 5%, 2 times 5% is 10%. And 2 standard deviation around the sides of the mean would give us the range from 10% to 30%. So I can say that with probability of 95%, the numbers drawn from a normal distribution with the mean of 20% and the standard deviation of 5% are between 10% and 30%. It's also nice to know that in a normal distribution with the probability of around 99%, the values would be within 3 standard deviations around the mean. So with almost certainty, any number drawn from a normal distribution would be within 3 standard deviations around the mean, which in our example means that the growth rate would be between 5% and 35% almost surely. I say almost surely since it's not still 100% sure. In fact, a normal distribution does not have any bound and it goes from minus infinity to plus infinity, although each of those numbers on the tails may have extremely low likelihood of realizing. This is in fact why in this plot we see almost no number out of these 1 million drawn that are below 0% or above 40%. But again, I highlight that the normal distribution does not have any bound and the likelihood that a huge negative or a positive number would be drawn from this normal distribution is not an absolute zero, although very, very close to zero. In fact, this is one reason that the normal distribution may not be the most suitable one for modeling some of the variables that we are uncertain about in our valuation. For example, if you have a variable that cannot be negative by definition, like a stock price or oil price and so on, you cannot use normal distribution for it. I must say that for prices, we should consider distribution like in log normal distributions, which has a lower bound of 0 and is skewed to the right, which means that it has a right tail. Here, let's also plot a log normal distribution, say for a distribution that the log of it is normally distributed with the mean of 0 and standard deviation of 1. It gives us the following plot. As you can see, its lower bound is 0 and is skewed to the right. Of course, you can change the parameters to match the distribution you would like to have for your variable. We will not discuss here log normal distribution in details, and hopefully in a later video we cover these types of distributions that are not symmetric. Other situations you may not be able to use a normal distribution is for variables that cannot be higher than a specific number. For example, we are typically uncertain about future operating margins for the company we are valuing, but we need to project them anyways in the future to be able to get our DCF value. In case you are not familiar with operating margin, it is the ratio of operating profit to sales, which measures what percentage of revenue turns to operating profit. For example, an operating margin of 20% means that 20% of the revenue turns to profit for the company. These margins by definition cannot be more than 100%. So strictly speaking, it's not appropriate to use a normal distribution for margins, since some draws for the margin will be more than 100% in a normal distribution. But as I will discuss later on, it's not uncommon to use a normal distribution for margins. In fact, since in case of margins, most of situations would look like what we have here, and the probability that the margin would be more than even 40 or 50% is very, very close to zero. So that's why we will still use it frequently. Another situation you may not want to use a normal distribution is for the cost of capital. A normal distribution would imply some negative numbers for the cost of capital and some very large numbers, whereas we are usually quite certain about the range for cost of capital, and it can definitely not get lower than zero, for example. Okay, to sum up, for which inputs we should use a normal distribution, we need to be relatively confident about the mean or the most likely outcome, and the positive and negative deviation from this average value should be equally likely, or the distribution of the variable should be symmetric. And remember that you need the 95% or 99% rule we discussed before related to normal distribution to decide about the standard deviation you should assign to the input. The second very useful distribution is the uniform distribution. In this case, we have a specific lower and upper bound for the variable, but unlike the normal distribution, the likelihood of each value to realize is the same within the range. So let's plot 1 million numbers from this distribution as well. Again, we use NumPy random, but here we use uniform, and then we need to specify the parameters, which are the lower bound and upper bound, plus the size or how many numbers to be generated here. Let's assume that the average is again 20%, but the lower and upper bounds are 10% and 30%. So here the average is the same as the normal distribution we had before, but as you see, all the numbers have similar likelihood of occurring. Such a distribution we use when we have a strong idea about the range of the input variable, but the likelihood of each number within the range is similar. This could be a range for our cost of capital, for example. We typically have an idea about the range for the cost of capital, say between 5% and 8%, and usually within that range all the numbers have the same likelihood of occurring. Or it could be about the market share of the company in the future, and we may have a plausible range for the market share, and we may not have any strong opinion about which one is most likely, and they may be all as likely as the other numbers within the range. Okay, so you get the idea when we should use a uniform distribution. When there is a specific lower and upper bound for the variable and the likelihood of realizing numbers within the range is relatively similar. A third useful distribution is triangular distribution. As the name stands, it looks like a triangle. Let's generate 1 million numbers from this distribution as well and plot them. We use triangular from NumPy and then pass the parameters. The parameters are the lower bound, the peak or the mode, and the upper bound. Okay, as you can see, it looks like a triangle starting from 10%, then it peaks at 20%, and then the upper bound is 30%. In a way, you can think of this distribution as a mix of normal and the uniform distributions. It's like a normal distribution since the probability of each value around the peak is lower than the peak, And as we get further and go more towards the sides, the likelihood goes further and further down. On the other hand, it has similarities with a uniform distribution since it's bounded with specific lower and upper limits. Of course, this does not have to be symmetric, and you could define the peak to happen anywhere in the range depending on what you would like to assume for your input variables, as you can see. And so now that you know the characteristics of these three distributions, you should be able to model almost every important input we typically have in a valuation model. There is no rule on which one to use for which variable, but as I discussed, some distributions may be more suitable for some variables depending on the possible ranges and the likelihood of values in the range. All distributions we discussed here are symmetric distributions except log normal, but you can of course have asymmetric distributions as well that we will cover them hopefully in the future videos. So you may ask whether there are further guidelines that help to decide about the choice or parameters of distributions for an input variable. One way to decide about the distribution is to look at the historical values for that variable. For example, if we are dealing with the growth rate in the first 5 years following the IPO, we could take a look at the historical growth rates for similar companies in their first 5 years after their IPO and get an idea about the growth rates for these similar companies, how they look like and whether they are more or less in the same range or there is a wide variation across them and so on. In another word, we look at the relevant data and try to figure out whether the distribution of it looks more like a normal distribution with a low standard deviation, a normal distribution with a high standard deviation, a uniform distribution with a wide range, a uniform distribution with a narrow range, and so on. So overall, collecting relevant data and looking at the empirical distribution of the data would be an important insight guiding us what type of distributions may be more suitable for the specific situation and the company we are examining. On the top of that, we need to have a good understanding of the company and the situation we are facing, and based on that, we can bring our subjective beliefs into play and decide what distribution is more appropriate in the specific scenario we are dealing with. For example, we could in theory use all of the three distributions we discussed for the future growth rates of the company, but the most appropriate one would be the one that matches the existing data best and also reflect our understanding and analysis of the specific situation, industry, and environment of the specific company we are dealing with. Finally, as a kind of rule of thumb, if I want to generalize, in most cases, it's appropriate to use a normal distribution for inputs such as margins where they could be also negative. Again, the issue would be that there might be margins based on this which is more than 100%, but it would really be rare since typically we have margins say around 10 or 15%, and hence it's practically impossible that a normal distribution around this generate numbers more than 100%. That could also make our final results problematic. Okay, that was the margins, and I suggested to use normal distribution, or you could use a triangular distribution if you really want to make sure to be bounded. Another uncertain input in any valuation model is the cost of capital, and for that a uniform distribution would be generally suitable. Moreover, one important driver of value and something we are uncertain about in our models is the future growth rate, and I think the growth rate could be modeled using a triangular distribution quite well. Finally, if you have to model prices or revenues, for example, log normal would be one of the best since these variables have a lower bound of 0 and are skewed to the right. Okay, this was it. I hope you find this video useful. I would really appreciate any comment you have about the videos in our channel. The contents of the videos in this channel are mostly about corporate finance, valuation, Python programming for finance, portfolio management, and the intersection of data science and finance in general. If you are interested in these types of videos, I encourage you to take a look at the other videos we have in the channel and also to subscribe to our channel to be notified about future videos. Again, I really hope this was useful for you and have a great day.